Many scientists have contributed to current understanding of the universe. The remaining videos go over some of those scientific models and concepts. Sometimes the theories presented in consecutive sections blend nicely following a chronological order. However, science development has never been smooth, seamless, or continuous. Some sections will deviate into completely new problems and theories that seem disconnected from previous sections. Only later we will see how those different topics came together to advance a particular scientific field. The theories are presented following the at-the-time concepts and knowledge but written with a more recent understanding of math, physics, and modern nomenclature. The theories sometimes competed with other theories, and only the ones that prove to advance the knowledge are presented. Obsolete theories are just briefly mentioned. Isaac Newton and Albert Einstein are among the top brilliant minds the world has seen. Each at their own time made significant contributions that propelled science ahead in many fields. This video covers Newtonian mechanics and Galilean relativity, and the next video covers Einstein theory of special relativity. Let's start with Newton. Sir Isaac Newton was born on December 25, 1642. His most important work is summarized in his book, Mathematical Principles of Natural Philosophy, published in 1687. This work consolidated many previous results and established the field of classical mechanics. To accomplish his work, Newton developed new mathematical tools known as calculus. The German mathematician Gottfried Wilhelm Leibniz is also co-credited for formulating calculus, though Newton's work preceded Leibniz's by several years. By any measure, Newton is among the greatest minds that ever lived. He died on March 20, 1726. Classical mechanics is the theory describing the motion of real-world objects. The description of objects' motion in time is specified by a small number of parameters, namely, their position, mass, and the forces applied to them. Classical mechanics uses what is called a frame of reference to specify an object's position in time. A frame of reference is a multidimensional grid with three spatial coordinates and time. It is impossible to show those three spatial coordinates axis and the time coordinate axis in a single two-dimensional drawing. This diagram, for instance, shows the position of an object in a three spatial coordinates frame, but time coordinate cannot be shown and is taken into account by writing the spatial coordinates as a function of time. In order to better visualize the time coordinate axis and how the spatial position changes with it, we will reduce the analysis to the laws of motion to a one-dimensional space. For this one-dimensional space, the frame of reference is a Cartesian graph with time and position as axis. The traditional way of presenting a mathematical function in a two-dimensional graph is to have the independent variable, in this case time, as the horizontal axis and the dependent variable, in this case the position, as the vertical axis. However, the common practice in special relativity and cosmology is to present the coordinate position x as the horizontal axis and the coordinate time as the vertical axis. The path taken by an object is represented by a line connecting the positions at different times. Newton's used calculus to define velocity and acceleration from the function describing the position of an object with respect to time. In a one-dimensional frame of reference, an object's velocity is defined as the derivative of position with respect to time. Similarly, the object's acceleration is the derivative of the velocity with respect to time. Therefore, the object's acceleration is the second derivative of position with respect to time. An inertial frame of reference, also known as a Galilean reference frame, is one that is not undergoing any acceleration. Acceleration is a change of the velocity vector with time. Since velocity is a vector in our three-dimensional universe, it can change direction in time as well as its magnitude. For instance, a satellite orbiting the Earth may do so with a constant speed around the Earth, but since the direction of the velocity vector is continuously changing, the satellite is accelerating. Since the Earth rotates around its axis and around the Sun, it cannot be used as an inertial frame of reference. Inertial frames of reference cannot be subjected to changes in their velocity vector in magnitude or direction. Newton's first law of motion as applied to the movement of an object in inertial frame of reference states that an object at rest remains at rest, or if in motion, remains in a linear motion at a constant velocity unless acted on by an external force. Newton's second law states that the acceleration of an object is directly proportional to the net force and inversely proportional to its mass. It can be seen as the definition of what a force is in Newton's mechanics. Or, using the definition of acceleration, the force is equal to mass times the second derivative of position with respect to time. Newton's third law of motion states that for every action, there is a reaction of same magnitude and opposite direction. In other words, when two objects interact, they exert opposite forces on each other that are equal in magnitude but opposite in direction. Galilean Relativity states that the laws of motion are the same in all inertial frames of reference. Newton used this as an axiom when he developed his laws of motion. Newton assumed that there exists an absolute frame of reference or absolute space in which laws of motion are true. Other inertial reference frames are in relative uniform motion to the absolute space. He also assumed that all inertial frames share a universal time with the absolute space. Some examples found in books describing Galilean relativity are misleading. They usually involve an observer on a train, or on a car or on a bicycle traveling through a familiar landscape and an object being thrown with a constant and known relative velocity to the observer. We usually infer a lot from the information we gather when go through similar experiences, but they don't fully explain the essence of Galilean relativity. For this we will imagine events that we are not familiar with so that we can reason without any preconceived ideas or data. Imagine you are a passenger on the black spaceship. You don't feel any acceleration, so you know you are either at rest or moving at a constant speed. You can't tell the difference. One other passenger is traveling with you. He is sitting in front of you. The distance between the seats is constant and equal to d1. This is your ruler for distances. Your spaceship will pass by two other spaceships that are at a constant distance from each other. Each spaceship carries a fellow passenger. They are also not experiencing any acceleration, so they also know they are either at rest or traveling at a constant speed. They can't tell the difference and neither can you. The passengers on the spaceships know the distance between them, but you do not. The distance between the passengers on the blue and red spaceship is constant and equal to d'2. This is their ruler for distances. All the clocks have been synchronized at a certain time in the past. Your and your fellow passenger frame of reference is your spaceship clock time and distances measured from your seat, namely t and x. For the passenger on the spaceship to the left, his frame of reference is his spaceship clock time and distances measured from his seat, namely t' and x'. The passenger on the spaceship to the right uses the same t' and x' frame of reference. All passengers can record their spaceship's time and the events that happen right in front of them. There is an astronaut equipped with a jetpack that was used initially to propel him. He is currently traveling without using the jetpack thrusters, so he knows he is either at rest or at a constant speed. He can't tell the difference and neither can you or your fellow passenger or the passengers on the other two spaceships. You are asked to determine the velocity of the astronaut with the jetpack. For this you do the following. You and the other passenger seating in front of you record the time the astronaut is right in front of both you, namely t1 and t2. With this information and knowing the distance between the seats, you determine the velocity of the astronaut as. Now the passengers on the other two spaceships do something similar. They record the time the astronaut passes in front of them, namely t'1 and t'2. And knowing the distance between them, they can calculate the velocity of the astronaut as v'. When comparing those two velocities, all passengers arrive at the conclusion that v and v' are different. The other two spaceships have also recorded the time you pass in front of each of their occupants, namely t'3 and t'4. And with this they calculate a relative velocity between you and them. But you and your fellow passenger have also recorded the times you pass right in front of the passenger on the red and blue spaceships, namely t3, t4, t5 and t6. With this you can determine the relative velocity of the other spaceships in relation to you. When examining the results you realize that those velocities are equal, which means that the blue and red spaceships are not moving in relation to each other. You have also compared the time of the events when you and your fellow passenger are aligned with the blue and red passengers, and the conclusion of this is that the clocks are still synchronized. This experimental result indicates time is universal and relative movement does not affect time. Comparison of the velocities Vr and Vr' yields the following experimental result. Using the time that you were right in front of the passengers on the blue and red spaceships yields. Comparison of the distances d2 and d'2 yields the following experimental results. This experimental result indicates that space distances are also universal and relative motion does not affect space or distances. Upon examining the first set of experimental data on determining the velocity of the astronaut with the jetpack, all passengers agree that the experimental data yields the following result. In essence, Galilean relativity tells us how to convert velocities of an object measured by observers in two inertial frames of reference that are moving with respect to each other. The gauges or rulers used for measuring time and distances are universal in special relativity. Integrating this equation we obtain, where the lower limits of integration are an initial time and the corresponding x and x prime positions at this initial time. The last term in parenthesis on the right-hand side is a constant. It is convenient to assume that the initial time is 0, and that at this initial time, the initial value of the spatial coordinates is 0. Only in this case the transformation equation becomes. This is valid when both frames of reference xt and x'(t) share a common origin. Frames of reference that share a common origin are said to be in the standard configuration. The standard configuration allows simplification of the math with no loss of generality in the conclusions. Usually, it is assumed that the coordinate x' is moving in relation to the coordinate x with a velocity vr. The relative movement of the frames affects how positions and movements are described in each frame. According to measurements, relative movement does not affect the spatial and temporal coordinate scales. Those quantities are universal and independent from each other. But this is an experimental result, and one may wonder if at very high relative velocities we would be able to confirm or deny an effect of relative motion on the way time and space are perceived and measured. This is indeed the case. Later we will see that at very high speeds, Galilean relativity fails. Our intuition of universal time and space is wrong, and a new approach to relativity will be needed. A proper or comoving frame is a frame of reference that is attached to an object or observer. The object or observer is stationary in this frame. In Galilean and special relativity, proper and comoving frames are synonymous. However, in cosmology, the terms proper and comoving distances have different meanings. We will now introduce the concept of world lines. Imagine an observer that uses an inertial proper frame of reference based on coordinates x and t. The observer remains at rest at the origin of the x-axis. Imagine a second observer that uses another inertial proper frame of reference based on coordinates x' and t. This second observer is always at the origin of his frame of reference, but his frame of reference is moving with relative velocity v with respect to the first observer frame of reference. Assume that at time 0, the origins of both frames of reference are the same. This picture shows the frame of reference xt for the first observer. The first observer world line is a line showing the positions of the first observer as a function of time. Since the observer is at rest, his world line coincides with the vertical time axis. When we think of events, we think on things that have a duration in time and location. In relativity, the concept of an event is an idealization and refers to anything that happens that has a specific time and place. Therefore, in relativity, an event specifies a definite pair of spatial and time coordinates. Imagine an event happening at position x and time t in the stationary observer frame of reference. The dashed line parallel to the x-axis intercept the vertical axis at time t. Similarly, the dashed line parallel to the stationary observer world line intercepts the horizontal axis at position x. The moving observer world line is a line connecting the positions of this observer in the xt frame of reference. The line parallel to the x-axis passing through the event intercepts the vertical axis at the time t. At this time, the traveling observer is at a position in the x-axis that is equal to the relative speed multiplied by the time. A line parallel to the moving observer world line, passing through the event, intercepts the x-axis at the coordinate x prime corresponding to the position of the event as perceived by the traveling observer in his x prime t frame of reference. Another way of expressing this is that the horizontal distance between an event at position x and time t, and the traveling observer position in his world line at the same time t, is equal to the distance x prime the observer perceives the event as happening at. Let's formalize this for two inertial frames of reference that move in relation to each other with a relative velocity vr, and see how other objects' velocity, acceleration, and forces acting upon it are perceived by each observer. The first frame is based on coordinates x and t. The second has coordinates x prime and t prime. However, t and t prime are identical to the universal time t. Imagine an object that is moving with velocity v in relation to the first inertial frame. Using the Galilean transformation, the object's velocity perceived by an observer using the second frame of reference is, or, since the frames are inertial, the relative velocity between them is constant. And we have that the acceleration of the object in both frames of reference are the same. Since acceleration is the same in any frame of reference, forces will be independent of the reference frame. Impulse provided by a force to an object is defined as, since force is independent of the frame of reference and time is universal, the value of a force impulse is independent of the frame of reference used. The linear momentum p of an object or particle is defined as the product of its mass and velocity. For an inertial frame of reference, the linear momentum is defined as, from the point of view of a frame of reference that is moving in relation to the stationary frame of reference, we have the following expression for the linear momentum. Therefore, the definition of momentum is independent of the frame of reference used, but the value of momentum depends on the frame of reference used. The force impulse on an object is equal to the change of the object's linear momentum. Therefore, although momentum depends on the frame of reference used, momentum changes do not depend on the frame of reference used. Newton's third law states that for every action there is a reaction of the same magnitude and opposite direction. Therefore, for particle 1 or object 1, the impulse exerted by force 1 is. For particle 2 or object 2, the impulse exerted by the reaction force F2 is. Defining the total linear momentum for both particles or objects as. Then we can write. When considering both objects together as a system, the total change in momentum is zero and independent of the reference frame used. A particle or object's kinetic energy is defined as half of the product of its mass and its velocity squared. For a stationary frame of reference, the particle's kinetic energy is. For an inertial frame of reference that is moving in relation to the stationary frame we have. Therefore, the kinetic energy definition is independent of the frame of reference, but kinetic energy values depends on the frame of reference used. Work done by a force on an object is defined as the force times the displacement of the object. The force is independent of the frame of reference, but the displacement is not. Therefore, The definition of work is independent of the reference frame, but the values of work done by a force are dependent on the frame of reference used. Work is equal to changes in kinetic energy. Therefore, changes in kinetic energy are also dependent on the frame of reference used. Imagine two inertial frames. The first, S, is based on x and t coordinates, and the other S' is based on x' and t' coordinates. The frame S' is moving in relation to frame S with a velocity vr. Consider a particle p at rest on frame x' t'. At a time of 0, the particle p splits into two smaller particles A and B. An observer using S' as his proper frame measures the velocity of the split particles as -vr and vr respectively. What we know from the statement is, we would like to determine the relationship between the particle masses, the velocities as measured from frame S, and the linear momentum expressions in S and S' frames of reference. Galilean relativity assumes that mass is constant and independent of the reference frame used. Imagine the mass of the split particles are ma and mb. The original particle mass is therefore. The velocity transformation equation in Galilean relativity is the velocity of the initial particle before the split is then the split particle's velocities as perceived by frame SR. Using the values of VA' and VB' we obtain, or the linear momentum before and after the split can be calculated in both S and S' frames of reference as, or and for the S' frame, or conservation of momentum on both frames yield the same results. In frame S we have, as a conclusion, and for S' we have, as a conclusion, and therefore we can write We will take the opportunity now to introduce a few more concepts that will be important in future videos. Galilean transformation equation relates the spatial coordinates for an event in inertial frames that are moving in relation to each other. In Galilean relativity, two distinct events are separated by a time interval delta t that is the same for all inertial frames of reference. Therefore, events that are simultaneous in one frame are also simultaneous in any other frame. Simultaneity is absolute in Galilean relativity. We can now define Galilean distances. The distance or length of an object is measured by simultaneously placing a ruler over the object's ends. The distance between simultaneous events is a positive quantity, and in our one-dimensional space it is defined as. Because of simultaneity, the distance measurements are not dependent on the frame of reference. Not only time is universal, but also lengths of objects and rulers are universal in Galilean relativity. Galilean distance equation can easily be extended to three-dimensional space infinitesimal line segment as, or in matrix form we can write. The 3x3 matrix is called the metric matrix. It is dependent on the spatial coordinate system used. For a Cartesian spatial coordinate system, the metric matrix is for the two-dimensional polar coordinates, the metric matrix is, and the line segment infinitesimal distance is. Some coordinate systems may not be orthogonal. For instance, in Cartesian coordinates, the angle between the x and y coordinates in 2 dimensions is 90 degrees. But if the angle is different, we have oblique coordinates. If the angle between the v coordinate and the u coordinate is theta, then the metric matrix is, and the line segment infinitesimal distance is. George Friedrich Bernhard Riemann was born on September 17, 1826 and died on July 20, 1866. He was a German mathematician who made profound contributions to analysis, number theory, and differential geometry. His doctoral advisor was Carl Friedrich Gauss. In 1853, Gauss asked Riemann to work on his dissertation on the foundations of geometry. Over many months, Riemann developed his theory of higher dimensions and delivered his lecture at Göttingen on June 10, 1854. The early reception of Riemann's work appears to have been slow, but it is now recognized as one of the most important works in geometry and started the field of Riemannian geometry, laying out the foundations of the mathematics of general relativity. He is considered by many to be one of the greatest mathematicians of all time. Riemann generalized those results for any arbitrary generic multidimensional space. For a three-dimensional space using any generic coordinates x1, x2 and x3, the metric matrix elements are the inner product of all unitary vectors in each of the spatial directions. The infinitesimal line segment in this space is determined as, or using Einstein's simplified notation where the summation terms are implicit. In relativity, an earlier event A and a later event B are said to be causally connected when something, let's say a particle or observer, at the time and location of event A can travel and reach the location of event B at the time event B happens. Imagine an event A located at the origin of a stationary frame of reference. Imagine also a second later event B that happens at location xb and a later time tb on the same frame of reference. Event A and event B are causally connected if a moving observer using the proper frame of reference x prime t is moving with a relative velocity given by the following equation. Since Galilean relativity does not impose any limits on velocities, all future events are causally connected to prior events. Simultaneous events are the only events that are not causally connected. For inertial frame of reference, proper time or clock time is the time a clock at rest at the origin of the inertial frame of reference will measure. Proper time is indicated by the letter tau. Since in Galilean relativity time is universal and is measured by the coordinate time, it follows that for all inertial frames in Galilean relativity proper time is coordinate time. Invariants are quantities or statements that do not change from one inertial frame to the other through the coordinate transformation. Let's see which variables and statements are invariant and which variables and statements are variant in Galilean relativity. Everything worked fine till the end of the 19th century when scientists started to see some problems with the concept of Galilean relativity. The problems were related to theoretical and experimental results related to the speed of light in vacuum. The theory and results pointed out that the speed of light in vacuum is a constant and independent of the velocity of observers measuring it. This is inconsistent with the Galilean relativity. The Galilean velocity transformation results in different values for the speed of light as measured by observers that are moving in relation to each other. This is the topic of the next video.